afternoon here, maybe good morning, good evening somewhere else from where our speakers are. This is our session 3, and this is last technical session before we'll close today webinar at 4:30. So this session is going to start at 1 o'clock, and it will be up to 3 hours 15 minutes. And we have 5 speakers. Out of 5, we have 3 international speakers and 2 internal speakers from KFUPM. So the external speakers will have 45 minutes total. That will include presentation as well as question answer session. And our internal speakers will have total half an hour time. So as we did in the previous session, we will collect the questions and allow the speaker to present. And then at the end, during 10-minute time, we'll invite questions, and the question I will read for the speaker to answer, and that way you'll get the answer. So we'll try to accommodate as many questions as possible, but within the time frame. So I would like to request the speaker to give at least 10 minutes at the end for question and answer, or at least 7 to 8 minutes. So as I said, there are 5 speakers. Our first speaker is Professor Muhammad K. Naziruddin from École Polytechnique Lausanne, Switzerland, and he is he has already he is ready now to deliver his lecture. But before he will go to start, I would like to give a brief introduction about Professor Muhammad Naziruddin. Professor Muhammad Naziruddin received his MSc and PhD in organic chemistry from Osmania University, Hyderabad, India. His current research is focused on dye-sensitized solar cells, perovskite solar cells, carbon dioxide reduction, hydrogen production, and light-emitting diodes. Professor Naziruddin was awarded EPFL Excellence Prize in 1998 and 2006. Then the Brazilian FAPESP Fellowship in 1999, Japanese Government Science and Technology Agency Fellowship in 1998, Government of India National Fellowship in 1987-1988. He has been appointed as world-class university professor by the Korea University, Korea, and adjunct professor by the King Abdulaziz University, Jeddah, Saudi Arabia. According to the Web of Science in 2016, Professor Naziruddin is the 5th most cited chemist in the world and is one of the 19 scientists identified by Thomson Reuters as the world's most influential scientific minds in 2015. He has been named by Thomson Reuters as a highly cited researcher from 2014 to 2020 and has been identified by the Times of Higher Education, the top 10 researchers in the world working on the high impact perovskite materials and devices. Professor Naziruddin has more than 700 research articles, and he has citations 133,348, maybe even more. It is, I think, 1 month old data, and he has H index 182. The title of his lecture is Perovskite Solar Cells, a New Paradigm in the Energy Sector. We are going to have such a great scientist in a few seconds. So I would like to request Engineer Sanaullah to share his file presentation so that he can start. So Professor Muhammad Naziruddin, kindly.
Dr. Shumshed, Professor Nazir can share his own if he wants.
Yeah.
Okay.
Yeah, I will share my slide.
So he will have a better control over it.
Okay.
Sure.
Yeah. Well, first of all, thank you, Professor Ahmed, for your kind introduction. Very elaborate. So I would like to start with thanking the organizers and KFUPM for this kind invitation to share our recent results on perovskite solar cells. And with your permission, I would like to share my presentation. The slides, can you see the slides?
Yes, we can see.
Let me go to the presentation mode, and then let me just open the laser pointer. Okay. So first of all, I would like to thank the organizers for inviting me to share our progress in perovskite solar cells. My presentation is tailored, particularly keeping in mind the young students. So you will see more details of the ways and the design strategies which we are applying in the perovskite solar cells. So this is more going into the chemistry. So maybe most of the students who are chemistry background will really benefit from this presentation. So the title of my talk, as you mentioned, perovskite solar cells, a new paradigm in the energy sector. Indeed, the way we are looking at the future, so the energy scenario, with this new technology, we will change the energy generation, the energy distribution. So you can imagine the way we are working nowadays with the telephones. That's a mobile phones everywhere compared with the 20 years old technology of the fixed lines. So the energy will be totally mobile and totally independent. You can produce wherever you want, and the energy supply will be grid free. So this is the future which we are looking towards this technology. So with this introductory remarks, so I will like to share my presentation. So this is my university, EPFL, that's a Ecolo Polytechnic Federal Lausanne. I'm also adjunct professor at King Abdulaziz University and world-class university professor at Korea University. On the bottom, you can see my email address. If you have any queries regarding my presentation, please feel free to send an email or to send any queries. I will be happy to answer as soon as possible. Now, this is our campus. It's a very nice campus. I just want to highlight, this is our Congress Center, which can accommodate 5,000 people. On the right side, we are having an innovation park. Here we have 10 new buildings where all the new technologies developed in the campus will be translated into the innovation park for the startups. Now, I just want to come back to the technology. So we have seen very nice presentation from Professor Martin Green. So here, the silicon solar cells which we have seen, the efficiencies are in 26% range. The perovskite solar cells, which you are going to listen from me, is 25% efficiency. But the difference in the processing and the energy input and the technological difficulties is huge. It's day and night. And if you look at the bottom left side, on the bottom left side, you have a silicon solar cells where you have to start from the metallic silicon, which you have to melt it and then process it and make it ingots and wafer it. It's a complicated technology. Cost-wise, we have seen the cost is coming down significantly, but technologically, this is rather complex and it's not feasible to many countries to start. It's a millions or $1 billion industry to start with. On the contrary, the perovskite solar cells is a very simple technology where you can use perovskite materials and process the solar cells by solution processing or even inkjet printing. Imagine tomorrow, if we produce solar cells like using the printing technology, the way we are producing solar cells, square meters and square meters, and we can produce the solar cells by using the printing technology. What do we have in this technology? What is the so difference in this technology, new technology, compared to existing silicon solar cells? So the new technology is a solution process, and the perovskite material absorbs, it creates charges, and you extract these charges between the two layers. One is electron transport layer, another is hole transporting material. And this is such a simple technology which creates the efficiencies comparable to silicon solar cells. However, you can also use this material for light emitting applications. That's for display technology. So this material has a beautiful property. It absorbs all the light, it creates charges, and at the same time, you inject the carriers into the perovskite material that gives you the light depending on the band gap of this material. So this is what this material's properties are. And I will highlight these properties as we go on. And then we see how the efficiencies of the solar cells can be improved. And the stability is one of the biggest criteria of these materials, which you will see in my presentation, how we are addressing. So what is perovskite actually? If you look at the perovskite material, it's a very simple composition. It's a ABX3. A is a simple monocation. It is either inorganic cesium, methylammonium, organic cations, formidinium. B is a metallic dication. It can be lead 2+, or tin 2+, and X is a halide. The combination of these three components gives you this beautiful material, and then the properties is highlighted here. They absorb visible light very strongly in the whole visible spectrum between 400 nanometers to 800 nanometers. Now you can change this material property by changing the material. For example, X, if I change iodide to bromide, it's a green emitting material. It absorbs in the visible region up to 500 nanometers. And if we remove bromide to chloride, it is an ultraviolet material. It emits in the range of 450 nanometers, blue emitting material. So you can change the same material. You can change the band gap by tuning either halides or to some extent either by cation or even the central metal 2+ cation from lead to tin 2+. So these are the materials which gives you the plenty of opportunities to tune its properties. The another very important property of this material is a small excitation dissociation energy. What is this property? Well, if you look at any absorbing material, when you shine the light, the absorbing material takes this photon, it creates charges, positive and negative charges. So this so-called positive negative charge is called exciton. This positive negative charges, they stay together. It's called exciton binding energy. Fortunately, in perovskite solar cells, the moment you shine the light, you create the charges dissociates and collects at the interface. So this is one of the beautiful property of this material that gives us such a high efficiencies without any losses. With this small the properties of this material, I will go to show you the real absorption spectra of this material. On the left side, you see the absorption properties of this material, where X is a halide, that's iodide. It absorbs all the visible region up to 820 nanometers. And wherever you excite, you get a very nice emission spectra around 780 nanometers. Another interesting property of this material is a sharp onset compared to a silicon solar cell material. That's an indirect band gap material. It has a sluggish onset, whereas in the perovskite, you have a strong onset, and this strong onset is an indication of the micros, which has a low trap density. So, and therefore, it can be useful for the perovskite silicon tandem solar cells to increase the power conversion efficiency beyond the 26%, which is around close to 30%. Very recently, Berlin group has reported. Now, if you look at on the left side is a cartoon. On the right side is a real cross-sectional image of our solar cell. So I just build the solar cell the way we have worked. So we take the conducting glass substrate, and then we deposit a compact layer of TiO2. Each of this layer has a functionality, and there is a task for each layer to perform. So the compact TiO2 layer reduces the recombination, and that's the reason why it's important to have a very thin layer of compact TiO2 layer, followed by we have a double layer of metal oxides, TiO2, tin oxide. So this is a very small layer, around 100 nanometers is shown here. So this particular layer is an interface between the perovskite and electron transport material. So the bilayer configuration we discovered is very important in order to stabilize this material. You will see in my presentation towards the end of my presentation. Now the perovskite, this is a perovskite composition. Here you have an opportunity to tune the composition so that you make this material extremely stable performing material. And on the top, we have a very thin layer of two-dimensional perovskite. This you will see in my presentation, what is two-dimensional perovskite, what is three-dimensional perovskite. So we deposit two-dimensional perovskite, very thin layer, followed by a whole transporting material. This is organic material, and then the contact. So this is the solar cell configuration. It's all solution processing. And this solar cell, when you make in the lab, it gives you close to 24.5% efficiency. And this efficiency, if you look at particularly the current, it's a 25 milliamps, and the VOC is extremely high, 1.15. How does it compare with the silicon solar cells, which are around 680 millielectron volts? So that's the reason why even if you have a low short circuit current, the efficiencies are comparable to silicon solar cells. So this cell we measured in the lab and we sent to Newport for certification, and there we got exactly the similar efficiencies as we measured in the lab. So this is the highest efficiency coming from our lab to show that these are the materials which has a high efficiency. Using this material, so we also went for the mini modules, which is 6.5 by 7 centimeters, and the efficiencies in the at present we are having around 18%. This mini modules, we hope to get this mini module size to 20 by 20, so that you can have a silicon wafers type of solar cells putting together, or eventually you can put perovskites on the top of silicon solar cells for tandem configurations. As I mentioned before, you can change the color of these materials by tuning either cations or halides. You can have a pattern of color so that for future building integrated applications, you can use this material to integrate into the buildings, so that the buildings will be power generating buildings. Those are called smart buildings. You can also have on the plastic substrates, so that the efficiencies are slightly lower, but still it's possible to have a flexible solar cells working in the same way as on non-flexible substrates. So that's a state of the art in our lab. But what is the problem? So you have heard in the morning, Professor Martin Green's talk, the perovskite materials are least stable, though the efficiencies are comparable to silicon solar cell, but the stability of these materials are very low. So how do we increase the stability? That's the reason why I made this presentation in such a way that the students will enjoy and then take this topic further by their imagination to come up with the new materials. So what are the ways you can increase the stability of this material? So I have highlighted 3 possible approaches. 1, interface engineering. What are the interfaces? Now let me take back to the initial stage. So here we have this is our perovskite material. So the interface between the perovskite and the whole transport material, this you can modify with the 2-dimensional perovskite. And the interface between the electron transport material and the perovskite, this is another interface. So these are the 2 interfaces you can target and then improve the stability of these materials. The second approach is change the composition of this perovskite material, absorbing material. So that's the second approach. And some of the charge transport materials which we are using or which are available in the literature, not perfectly stable. So can we target and make these materials, new materials, so that the whole solar cell is extremely stable? So now I go back to my presentation. So the topic today is how to improve the stability, either by interface engineering or by compositional engineering of perovskite materials or development of charge transfer materials. You will see in this, my presentation, highlighted slides of each section. Okay, now let me just go back. So this is the 3-dimensional perovskite, where when we have a ABX3, the cation size is fixes into this cavity, it forms a 3-dimensional network. What happens if we increase the cation size beyond the cavity? Then you slice this 3-dimensional perovskite into low-dimensional perovskite as shown here. Now, depending on the amount of bigger cation, you can have a n equals to 2 or n equals to 3, n equals to 1. So now it all depends on the tuning of your smaller cation versus the bigger cation. So what are the bigger cations you can think of? Let me just take out this one. So what are the big cations you can think of? So on the right side of this panel, I'm showing the possible the cations, N-butylamine, isobutylamine, all these are the big cations. They also form a two-dimensional, the perovskite structures. When you have a bigger cation, which does not fit into the cavity, they form a two-dimensional perovskite. They are extremely stable. That's the reason why we are working with this material. But the drawback you can see from the bottom panel, the three-dimensional perovskite absorbs the whole visible region up to 820 nanometers. On the contrary, the two-dimensional perovskite absorbs only a small portion of the visible light. But this is extremely stable material, and the three-dimensional perovskites are less stable. So the combination of this three-dimensional perovskite and two-dimensional perovskite can stabilize the perovskite solar cells significantly. That's what I'm going to present. So here is the one cation we have selected. So this is our perovskite composition, where we are having a triple cation, cesium, formidinium, methylammonium, and double anion, iodide, and bromide. This is our basic composition of the perovskite layer. Now we deposit on the top of this perovskite, three-dimensional perovskite, a two-dimensional perovskite layer, which has a phenylethylamine as a cation. So now each perovskite has its characteristic features. If you look at the XRD spectra of the two-dimensional perovskite, is shown here. This is a characteristic peak of two-dimensional perovskite. And at 14, we have this is another characteristic fingerprint of three-dimensional perovskite. Now, if you look at your final structure, two-dimensional perovskite deposited on top of three-dimensional perovskite, now you can see the presence of two-dimensional perovskite peak, at the same time presence of three-dimensional perovskite. So these are based on the X-ray XRD data. If you look at the visible spectra of UV visible spectra, the two-dimensional perovskite, as I mentioned before, it has a absorption in the visible portion, very small visible spectrum it absorbs, and the black line is a total three-dimensional perovskite, and then the red curve shows the absorption spectral properties of two-dimensional perovskite deposited on top of, three-dimensional perovskite. On the top, we have a two-dimensional perovskite. So these are the two characterization technique. And the third technique which I'm going to show you is, so since the two-dimensional perovskite has a typical absorption in the around 520 nanometers, now you can excite from the top side to see whether we have a two-dimensional perovskite on the top or it's in the bulk. Now you can clearly see by exciting from the top side, you see the only emission coming, majority of the emission is coming from the two-dimensional perovskite. But however, since the laser power is slightly higher than the two-dimensional perovskite layer thickness, it touches the three-dimensional perovskite, you can see a small peak coming from the three-dimensional perovskite. At the same time, compare the same material without two-dimensional perovskite and excite from the same wavelength, you see only the presence of three-dimensional perovskite. On the contrary, take the same two cells, a reference sample, followed by the two-dimensional perovskite deposited on the top of three-dimensional perovskite, bottom side excitation, the overlapping emission spectra clearly shows that we have created a layer by layer deposition of three-dimensional perovskite followed by two-dimensional perovskite. So, well, this is very interesting, but what is the advantage of having this two-dimensional perovskite on the top of three-dimensional perovskite? Just before I go to show the advantages, just look at the energetic scheme of these materials. By using UPS data, we build the energy level scheme of the three-dimensional perovskite, two-dimensional perovskite, followed by the whole transporting material. If you look at the HOMO level of the three-dimensional perovskite, which is well aligned with the HOMO level of the two-dimensional perovskite, which is slightly below to the whole transporting material. So what is happening is, when you shine the light, you create charges within this perovskite. The holes are extracted. You are creating a channel to transfer positive charges towards the whole transporting material. On the contrary, the electrons which are generated here, they are not tunneling through this two-dimensional perovskite because the LUMO level is slightly higher than the three-dimensional perovskites. So the electrons are driven towards the ETL layer. So indirectly, we have created channels to extract positive charges on the one direction, negative charges on the other direction. Well, how do we know that this is happening? Let's take at the photovoltaic properties. So take the reference sample, only three-dimensional perovskite. the open cell potential is 1.09. The moment we deposit two-dimensional perovskite, the VOC increased from 1.09 to 1.14. So the small increase for you looks maybe nothing, but this increase is coming from the reduced recombination at this interface due to the creation of this whole therapeutic material in between the perovskite and then the spirometal. As a result, you can also see slight increase in the short circuit current from 21.8 to 22.73. So the net efficiency of the modified layered structure, it gives you close to 21% compared to 18.65% efficiency as a reference sample. Now, I show you the beauty of this two-dimensional perovskite compared to pure single three-dimensional perovskite. So here there are four curves which I'm showing. The two are without the reference samples. The empty circles are the measured under argon atmosphere without two-dimensional perovskite. The stability data up to 800 hours, it's decreasing significantly. However, without argon conditions, under normal environment conditions, but encapsulated, you can see it's decreasing significantly. The moment we deposited two-dimensional perovskite, in both the cases, under argon atmosphere, that's an open space, and open environment, but encapsulated, they overlap the stability data up to 800 hours. So this is the beauty of having two-dimensional perovskite as a protecting layer on top of three-dimensional perovskite. Now, I come back to the another interesting property. Perovskites are hygroscopic. It's just like the sodium chloride, salts. It takes a lot of water. Can we create intelligently hydrophobic two-dimensional perovskite so that they can be extremely stable? So here are the two cases I'm giving you the examples. One is a fluoride. Fluoride is a hydrophobic substitution. The fluorophenylethylamine, perfluorobenzylamine. So these are the two cations. If you look at the two cations absorption spectral properties of two-dimensional perovskite, the green one is the fluorophenylethylamine, which absorbs around 520 nanometers. And then the purple one is a perfluorinated benzylamine, which absorbs up to 480 nanometers. Now, similarly, we deposited on top of three-dimensional perovskite. The black line is a reference sample. You don't see much difference in the visible region, but in the UV region, you see a small increase due to the two-dimensional perovskite. That's a fluorophenylethylamine, and the red is perfluorophenylethylamine. Now, just compare the photo without going the characterization technique because it's the same as before. So we directly go for the photovoltaic properties. Take the reference sample, which gives me 1.09 volts, and the efficiency is 20%. The moment we deposited the two-dimensional perovskite layer on top of three-dimensional perovskite, the VOC went from 1.09 to 1.13. The power conversion efficiency increased from 20.2 to 21.31. Now go back to the fluorinated cation, perfluorinated cation or pentafluorinated cation. So the VOC further increased from 1.09 to 1.15. And then the power conversion efficiency went from 20.22 to 21.65. So here we are doing two things. We are increasing the efficiency because of the reduced recombination. At the same time, if you look at the stability data, this is the reference three-dimensional perovskite, the black line, it's decreasing over the time. On the contrary, the moment we have a perfluorinated phenylethylamine two-dimensional perovskite deposited on the top of three-dimensional perovskite, the stability is extremely high. So this is the beauty of these studies. So there are skepticism in the literature that the perovskite unit, are they stable? Well, the answer to this question is the perovskite materials are stable. So this is only by modifying the interface. So more details you will find a recent publication of Advanced Sciences in 2020. This is the reference given here. Now, compositional engineering of perovskite layers. So if you look at what are we doing? So here we have a three cations. I'm just taking an example. Methyl ammonium, this is one cation. Formidinium is a second cation. Guanidinium is another cation. So among these three cations, methyl ammonium and formidinium, this forms within this tolerance factor, where you can form a cubic three-dimensional perovskite zone. This is the three-dimensional perovskite zone. The moment we increase the size of the cation from the formidinium to guanidinium, so increase the size of the cation, you destabilize your perovskite solar cell. At the same time, if you lower the cation size smaller than the 0.8, it also forms lower dimensional perovskites. So can we come up with a intelligent strategy where we can combine the smaller cations and then the bigger cation, finally come up with a stable performance? So here is the one case we are showing. So we have combined 75% of methylammonium cation, that's a smaller cation, which forms the cubic structure of the three-dimensional perovskite. At the same time, we are mixing 25% of guanidinium cation. So having this ratio of 25% and 75% smaller and larger cations, the efficiency at that time, 217, was very high, 20%. Today we are at 24%, but at that time it was 20%, is quite high. But if you look at the stability data shown on the bottom, the black line is a pure methylammonium perovskite structure, stability over 1000 hours. The red curve is 25% of guanidinium incorporated as a cation. That shows you significantly enhanced stability of the perovskite materials. So this is a second approach which we are trying to come up, stabilize the perovskite by changing the composition of these materials. So I take another example. So can we modify the composition by coming up with a the hydrophobic ionic liquids? So here at this stage, people who are experts in the perovskite solar cell, I would like to mention the hysteresis is one of the problem. This problem is because of the ion migration. So here we are targeting two aspects: reduce the hysteresis by incorporating ions from outside, similar to ionic liquids as shown here. And secondly, since perovskites are hygroscopic, we are incorporating hydrophobic ionic liquid, and that forms a shell. You will see in my presentation in the next slides, that forms a shell protecting the perovskite significantly. So here instead of going each slide, the absorption spectral properties are the same when we have a reference sample, 1 to 4% of ionic liquid, because it's not changing significantly. But however, if you look at the characteristic peak of at this 12.6, this is a formation of lead iodide due to the decomposition of the perovskite. And if you have a three-dimensional perovskite without any additives, you say this is a lead iodide formation. When you incorporate even 1% of this ionic liquid, the stability is increased significantly compared to a reference sample. And if you go to the 2%, that's a green line. So you don't see any formation, small formation of lead iodide. If you go to 4%, it's practically lead iodide formation is suppressed significantly. What does it tell you? So having this type of ionic liquid in the composition, you can enhance the stability or decomposition of your perovskite materials. So, but the question is, what is this perovskite material, this ionic liquid is doing? So here is a very simple demonstration that even though we are having only 1% of ionic liquid at 50% humidity, 2 months, if you keep outside, front side and back side with 1% ionic liquid, the perovskite material shows extremely stable behavior. On the contrary, if the moment you don't have this ionic liquid, the perovskite, they get decolored. So this is the beauty of modifying the properties of the perovskite materials. Now I come back to the efficiencies, though the efficiencies are in the range of 20%, but the beauty, what I want to show here is, what is this ionic liquid doing here? So now we went to the XPS analysis. This is our analysis to show the fluorine binding energy. And now we take our perovskite grain with the focused ion beam, you just dig up to 75 nanometers. In the beginning, 0 nanometers, we do see the fluorine binding energy, which is the same as the reference. And up to 25 nanometers, you still see the fluorine, presence of fluorine, and 50 nanometers, it's almost gone. So this data clearly demonstrates what happens is, when you use this type of ionic mixed fluorinated hydrophobic ionic liquids, it forms a shell on the top of perovskite grain. And this particular shell is protecting this material from decomposition. So sorry, I went to back to this one. Yeah. So now I take another example, and this is the stability data, which is the moment we have this ionic liquid, it enhances the stability compared to without ionic liquid. Now I take another example just to show that this type of ionic liquids, first one is the fluorinated, that's a hydrophobic. And the second example I'm taking is again ionic liquid to suppress the ion moment. And at the same time, we are taking this ionic liquid functionalized with the double bonds so that they form a polymer composition. So here, again, we show you the initial efficiency 15%. By using this ionic liquid, you can increase 17% using very unstable composition of the methylammonium iodide perovskite. And using other perovskite composition, that's a formidinium and methylammonium. This is a very interesting stable composition, and this is the reference sample. The moment we use 2% of ionic liquid, we increase the power conversion efficiency from 19 to 19.20% efficiency. But the beauty here is when you take the functionalized ionic liquid, which has the double bonds, you create a similar ionic liquid without functionalized group, that's a no polymerizable group. Now you add the same amount, 2% this one and 2% this type of ionic liquid. Now you look at the beauty of this perovskite solar cell performance. Over 2000 hours, the stability of the perovskite solar cell remained over 90% of its initial efficiency, having the polymerizable ionic liquid. The moment we replace this double bond by a non-polymerizable group, and you can see the decrease in the efficiency is dropping to 40% of its initial efficiency. So it's a creation of the compositional engineering of the perovskite that gives you enhanced stability. Now I come to my last section, that's a development of charge transport materials. So spirometad, this is the molecule which is shown here. This is quite efficient but unstable. So, and because this has a lot of dopants. To work this spirometad as a whole transport material, we have to use cobalt complexes as a dopant, lithium TFSI, tertiary butylpyrene. So these are the dopants which make this material highly doped so that you have increased the conductivity. But the moment you dope these materials, you increase the hygroscopicity as mentioned, as measured by the contact angle measurements. So this, besides this hygroscopicity, and there is another drawback of the pyridine, which is we are adding into the system, is also attacking, self-attacking to the whole transport material, and that makes you the perovskite solar cells, the moment you use this type of materials, unstable for the long-term stability applications. So now we came up with can we design and develop new whole transporting materials that doesn't need any dopants? So here are the three cases which I'm showing. That's a C1B1, C1B2, C1B3. In all these cases, we have a similar core and 3 arms with the thiophenes. It all has a functionality. I will, if somebody is interested, please send me an email. I will write what are the purpose of all these materials. But in any case, just to remember, these are the 3 molecules which we have developed as a non-dopant whole transporting material. And the data is shown here. Just compare with the 2 data sets. One is the red one, that's a spirometad. With the dope, the perovskite solar cell efficiency is decreasing significantly. And our new molecule, that's a C1B3, both are having the similar efficiency as the spirometad, but the difference here is spirometad 18% efficiency as a reference with dope, and the newly developed dopant-free whole transport material also giving almost same efficiency, but the difference is dopant-free. So I come very quickly on the ETL side. Here also you can have a lot of ongoing research. So electron transport materials, we developed tin oxide using this acetonate type of ligands. And this type of material is very important to stabilize the perovskite and ETL layer interface. Using this ETL layer, new materials, we obtained 22.2% efficiency, which was again certified at Newport. And this is the data coming from the Newport, and this is data from our lab. Now, the importance of this tin oxide is shown here. Now, if we use only titanium dioxide, the perovskite solar cells are decreasing their efficiency significantly over the period of 1000 hours. The moment if I create pure tin oxide as electron transport material, the stability is significantly enhanced compared to the TiO2 layer. Or if I use TiO2 followed by passivating layer of tin oxide, again the efficiency is overlapping similar to the tin oxide. So the take-home message for the electron transport materials is TiO2 is a very bad material as electron transport material to have a stable interface between the perovskite and electron transport material. With that one, I come to the conclusions. So what I have showed today to motivate students is create two-dimensional and three-dimensional composite that delivers exceptionally gradually organized multi-dimensional structures that are very stable, that we have shown demonstrated. A new perovskite composition based on guanidinium. Now the people may ask, what is the purpose of guanidinium? If you look at the guanidinium structures, we have three NH2s, so it enhances the hydrogen bonding. So creating this guanidinium and methylammonium composition enhances stability and the performance. Hydrophobic ionic liquids, which I have shown you, clearly demonstrates very stable performance. And we developed dopant-free whole transporting materials that are comparable to spirometite. So with that one, I would like to thank my PhD students, postdocs is mentioned here, and international collaborators mentioned on the right side. And then I will go back to the work people, the students who really performed this work. I would like to thank all of them and thank you for your attention. I will be delighted to answer if you have any questions.
So nice of you. Thank you very much, Professor Naziruddin, for your very nice presentation. Alhamdulillah, this gives an idea how to relate materials with energy. And I think all the participants might take benefit of this information. We have 3 questions. So I would like to read these questions and kindly give your response one by one. The first question is, what does it make the perovskite not cost effective? Is it scarce or difficult to obtain? And this question is about the cost effectiveness of this material.
Yeah.
Go ahead.
Yes. Well, thank you for raising this very pertinent and important question. Fortunately, the perovskite materials, that's a lead base, it's a byproduct of the platinum group metals. So in fact, if you want to buy this material, the mining industry will pay you money to take this material. So this is a byproduct from the platinum group metals. So this is a very available material everywhere. So the cost-wise, it's insignificant. And availability point of view, there is a plenty of this material. And each square meter doesn't require more than 500 milligrams of the lead. So it's a very efficient thin layer material.
Okay, so next question is, how can I get a high homogeneity perovskite layer? Also, how we can solve the limited coverage? This is the question. Shall I repeat?
No. I got your question. I got the question. So
go ahead, Professor. Go ahead.
It's also an interesting question. So there are several techniques and several groups who are developing to get the homogeneity of this material. So there are, for example, blade coating technique. Spin coating is very interesting. The lab scale, you can produce up to 10 by 10. But if you want to go beyond 10 by 10, spin coating technique is not viable because you lose a lot of material. The blade coat technique is one which is coming up, and the slot die coating also is coming up. So these are the two large scale applications. You can have uniform coating. And the new technique which several groups, including the American groups, are producing is a spray type of deposition. So for the uniformity, these are the 3 techniques which can be applied. Spray coating, blade coating, slot die coating.
Yes, Professor. The next question is that our senior professor from KFUPM, he's asking, his concern is he's highlighting the disadvantages associated with this material, and he's saying that what about the efficiency which is not high, uh, 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 not high as organic, and lead-based PSC. Thanks.
Yeah.
His concern is the disadvantage, how to deal with the disadvantage and make it applicable, and coming soon to the market.
The
In
only,
short, yeah.
yes, yeah. The only disadvantage of perovskite materials was the instability. This is the biggest problem. So, including my group and several groups are targeting to improve the stability of these materials by different approaches. As I showed you systematically, by incorporating by interface engineering and compositional engineering, we can improve stability significantly. This was the only drawback few years ago. However, there is another drawback, which is a toxicity of the lead. But the European regulations, since the amount of lead which we are using, the thickness of perovskite layer is 500 nanometers. And within this 500 nanometers, the amount of lead is insignificant. So regulations are that it may be acceptable, but however, and this gives us opportunity to come up with the new materials to deposit on top of perovskite. If there is an accident, this new material, that's a new layer. For example, this morning we heard from SABIC, that's a metal organic framers, can be a very interesting material to absorb this lead so that you can avoid the accidents.
Yes, okay. Yes, Professor. The last question is again about some limitations. The question is environmental issues of perovskite solar cells as lead-free PSC are still suffering from either low stability or low efficiency. Please update on this. This is the
Yeah.
last question. Yeah.
Yes, I understand the problem because like your colleague and ourselves and the whole world is working, and including Professor Martin Green this morning, he was mentioning that they are trying to come up with the lead-free perovskite materials. Whoever comes up with the lead-free perovskite materials with the same efficiencies, I think they deserve very high appreciation. It's very difficult to come up with the same materials with the same efficiencies because of inherent interesting properties of the perovskites, which I showed you that it has a very nice absorption properties, low binding energy, all these properties creating in lead-free perovskite materials is rather difficult.
Okay, so I am sorry, another two quick question, two more remaining. This question again is about comparison of this material perovskite with the silicon-based material in terms of material toxicity, device hysteresis, and mechanical and chemical constraints. Just a comparison with silicon-based energy material. Yeah.
Yes. The first, we take the efficiency point of view. Both are the same efficiency. Second, complexity of the producing the silicon solar cells versus perovskite solar cells, extremely easy, extremely difficult. Now, compared to the stability, silicon solar cells has proven they are extremely stable. Perovskite solar cell has to be proven its stability and its performance under outdoor conditions. So there is a possibility that one day we may come up with a outside demonstration. So this aspect is a negative towards perovskite, and the silicon solar cell extremely stable. It has shown the performance outside conditions. Now, coming back to the mechanical properties, of course, silicon material is extremely stable material. Mechanical stability is extremely high. It's because the thickness is 300 micrometers. Perovskite materials, mechanical stability is very weak because it's a soft material and the thickness is 500 nanometers. So this is the drawback of the perovskite material. Advantage as well as drawback, because mechanically you need a lot of strength. It doesn't help.
Yes, Professor. So again, last two questions because already we are late by 5 minutes. So the next, he's giving you thanks a lot for the great talk, and he's asking, what is the mechanism that will increase the stability when you combine two-dimensional into three-dimensional route?
Yeah, this he pointed out correctly. When we use the three-dimensional perovskite, the three-dimensional perovskite is just like a salt. It takes water from hygroscopicity. It has a lot of disadvantages. So what we are doing is we are covering the perovskite, very thin layer blanket of two-dimensional perovskite, which we are creating the functionality of the two-dimensional perovskite, and that's a hydrophobicity. So that's the advantage of having the two-dimensional perovskite. It covers the three-dimensional perovskite, making it more stable.
So last question, Professor. Which is the best techniques to apply the TiO2 layer?
TiO2 layer, well,
Yeah.
right now, many labs are using spin coating method, but you can use screen printing technique.
Yeah. Okay. So nice of you, Professor. Thank you for your very nice talk and timely response to all possible questions. And we are honored to have such a person of this high caliber. So nice of you. We would like to see you again in future, in a very near future. Thank you very much. Yeah.
Thank you for your kind comments. Thank you.
So nice. Yes. Okay. So I'm going to move to our next speaker, who is from KFUPM, Professor Fahad AlSulayman. Professor Fahad Sulaiman holds BSc honors and MSc in mechanical engineering from King Fahad University of Petroleum and Minerals. He did his PhD in mechanical engineering with sub-specialization in energy systems, economics, and efficiency from the University of Waterloo, Canada. He had also worked as a visiting professor at MIT, the National University of Singapore, and the University of Oxford, a visiting researcher at the Canadian National Research Council, and a visiting consultant at Saudi Aramco. Professor Ahmed AlSulayman presently is the director of the Center of Research Excellence in Renewable Energy, and he is the founding director of the Center of Excellence in Energy Efficiency, both at KFUPM. He is a founder and mentor of the Students' Energy Club at KFUPM. He took the initiative to develop programs and courses in renewable energy and energy efficiency, certified energy manager, and certified energy auditor by the Association of Energy Engineers. And in addition, he's a certified trainer for CEM and CEA. He participated in so many projects and has more than 150 high quality research articles, and his citations are 4,766, H index 40, and he has 10 patents. Professor Fahad Sulaiman is going to make his presentation on water desalination using renewable energy, future and challenges. Professor Fahad AlSulayman, you are welcome to start your presentation, please.
طيب السلام عليكم ورحمة الله وبركاته. Thank you, Dr. Ahmed, for the introduction. First of all, I'm really glad to be invited for this forum. I would like to thank the organization committee, Dr. Ali, Sheikhi, Dr. Dirish, and also the session chairman, Dr. Ahmed. So today I'm going to talk about water desalination using renewable energy, future and challenges. And the outline of my presentation, I'm going to give some introduction about the water status in the world and the needs to find solutions. Also, I'm going to talk about the progress of renewable energy and water desalination. And I'm going to highlight on some challenges of renewable energy, water desalination, and some solutions, and what KFUPM did to find solution for, in general, water desalination and specifically solar or renewable energy driven systems. So just to take a general look to the status worldwide, as you can see, many countries, including Saudi Arabia, is considered on the extremely high risk of water shortage or stress in general. And in general, there are other countries which have some stress, mainly in the MENA region. You can read the number here, around 12 out of 17 most stressed water country in the world are in the MENA region. So we need really a critical solution for desalinated or drinkable water to our countries. In general, Saudi Arabia also is ranked number 8 in the shortage of adequate water according to water risk according to Atlas. In addition, other numbers here or statistics, as you can see, is not just the water production. You have to think about treating the water or wastewater. So around 82% of the amount of the water or wastewater in the MENA region is not reused. So we are just, we have misuse of water. In general, in Saudi Arabia, what is more important for our discussion in Saudi Arabia, for example, is the government introduced what is called Qatra program. The Qatra program is, the aim is to reduce the consumption per capita. Currently, the consumption per capita around 300 liters per capita, and the country would like, or the government would like to reduce this one to 200 per capita. And this is, so this fact, or there is a plan from the Ministry of Environment and Water toward this initiatives. On the other side, also around 44% amount of treated wastewater in the Gulf region is reused, and for different purposes. And also for the wastewater, we are treating most of it in the Gulf region. We are most of the wastewater, which is around 82%, is treated to safe level in the GCC countries. So it could be reused or just dropped in the sea or some other, or in the desert without reuse, but still in the safe level. So if you think about the economic point of view, around from 6 to 14%, because of there is water stress, it can impact the GDP for any country, and it is expected to impact, it will impact the GDP by from 16 to 14 by 2050 in the MENA region, according to World Bank. So there is a critical need to find solution. If you just focus down to Saudi Arabia, first of all, Saudi Arabia and as well many other countries in the MENA region and other big countries in addition are located in extreme arid region with limited water supplies. And indeed, we lost a good amount of water, groundwater resources, especially the one close to the ground level. And we are moving for future plan, especially like Vision 2030. We are expecting there will be increment in the population, there will be industrialization. So this will increase the demand of water. And in brief, there will be a gap between the water or the supply and demand, as you can see here. And in terms of numbers worldwide, half of the world population is already experiencing severe water scarcity at least 1 month a year. So it is a global problem. It is not local problem. And still there are some people where they have shortage of drinkable water. So it is, we need a solution for that one. And we need an efficient solution which doesn't consumes fossil fuel. We need green solution. If we just think also about the future, by 2030, around there will be increment of energy consumption around 50%. And in terms of water, there will be increment or increase in water consumption by 84%. So there will be demands, increment in the demands. This will make our self under stress to find solution. If we just think about the overall picture of power plant and desalinated water, in this curves, as you can see here, it shows the desalination capacity, and it is approaching now around 100 million cubic meter per day. And in terms of plant, it is almost the total capacity, it is almost reaching 20,000. So there is, and if you just take a look to the curve, it shows there is really, the slope is relatively high, and it will continue with this trend in the future. In terms of technology, it is mainly RO technology, and of course, which is the future. In addition, still there are some countries which is using MSF, MED, and ED. Moving forward, if you just think about the bigger picture, the MENA region, which is Middle East and North Africa, is consuming or producing almost half of the desalinated water worldwide. And it is mainly Saudi Arabia, UAE, in addition to Kuwait and Algeria. So there is a critical need to find solution worldwide. Now, is renewable energy a feasible solution? What is the status of renewable energy worldwide? And the figure here is showing you the annual addition each year, how many gigawatts is added in terms of solar, PV, wind energy, hydropower, and biopower. In general, you can see the solar energy is continuously increasing each year, and PV system, it is almost 115 gigawatts PV system installed worldwide. In the other side, there is around 60 gigawatt of wind, and also the hydropower in the lower side, which is almost 15 gigawatts, and biopower is around 10 gigawatts. But here we are just talking about power or electricity production. Now, if you would like to take a look, what is the status, for example, in Saudi Arabia, we have very ambitious program and plans is to have by by the end of 2024, this is by, they extended 1 year more, we are going to have around 27 gigawatts, and by 2030, we are going to have almost 59 gigawatts of renewable energy, and mainly it will be from PV system, and partially, and the rest will be wind energy, and small portion will be in CSP. And these are just the first, these are the 2 mega projects in Saudi Arabia. The PV system is working already, and this wind energy or Domat al-Jandal, which is 400 megawatt wind power, is almost ready to be commissioned. And meanwhile, of course, for our plan here, or for the government plan, several new projects have been awarded already, and it's about to start the commissioning, about to start the construction. Now, before we go about some examples or real application of desalinated, renewable energy desalinated plant, I'll give just a general picture about the technology. So briefly, you will have the input as saline water or brackish water. You need to desalinate it to get fresh water, and of course you will have some brine. And there are 2 options. Either there are commercially desalinated processes, like either it could be thermal paste, which is thermal process like multi-stage flash distillation, multi-fix distillation, or vapor compression, or it could be membrane-based, which needs usually electricity to run it, like RO or electrodialysis. These are the commercially available desalinated plant. If you think about the emerging technology or potential technology, is HDH desalination, where KFUPM have really advancement in this one, and they contributed in many new ideas and patents. We have also growing research worldwide and in KFUPM in membrane distillation. And of course, there are other technology like forward osmosis or CDI. And these one are usually is used for small and medium scale, for the at least for the current time. Now, if you just think about renewable energy as a source to get this desalinated water, We could have geothermal. When you think about geothermal, you have to think only thermal-based desalination plants like MSF, MED, MD, HD, or MED, TVC. And when you think about solar energy, you will have two options, either thermal-based, again, the same technology here, or electricity-based or PV system, where you could have, where you will produce electricity, then you can run RO or ED or MVC. Wind energy, as you know, it can produce electricity, or wave and tidal can produce electricity. Now, moving forward, the status, what is the status of operated renewable energy desalinated or desalination technologies? The figure here showing this mature level of the research or application, so that some technology is in the basic research level, some of them in the advanced R&D level, and some of them already applied recently or even since long time, like solar cells. And on the x-axis, what you see here is the power, the amount of or the capacity of the technology, how many liter can produce per day. And in general, the much mature technology is solar cells. Still, it is relatively, the main drawback for this one, it requires a huge area, and the cost is from $1.3 to $6.4 per cubic meters. And the main disadvantage, it is only used for small scale. Startingly to have relatively large and or medium scale plant, which is photovoltaics RO systems. And we have one relatively large in Saudi Arabia, which I'm going to discuss it soon. And also the other one, which is also has been tested in for medium and small scales, or you can say demonstration scales in many places, including here in Saudi Arabia, is solar CSP plant. And for the advanced R&D, we have solar multi-effect humidifications, which is relatively can work for small and medium scale, and still the price is relatively expensive. We have also wind RO, which is can be used for medium scale. And just moving forward down, we have also solar membrane distillation. However, still it is relatively expensive. And we have wind mechanical vapor compression, and which is relatively also expensive. And we have other technology like solar organic seawater RO, wind ED, and wave RO. So in the top of the figure here, these are promising technology and either demonstrated or it has been already tested in real scale or large scale demonstration levels. Now, if you, as I mentioned before, BVRO is relatively well established and it has been tested in many places, including Saudi Arabia. And the principle is you have regular RO system or conventional RO system, and you need just electricity source, which is PV, and you need battery to have stable operation for the pump and for the desalination, for the RO system. So in Saudi Arabia, it has been tested and it has been proven working in Al Khafji area, which is close to Al Kuwait border. It has been tested. At the beginning, they have some challenges indeed, including the technology of PV system. They change it from CPV to flat plate with tracking option, and now they are getting the electricity for Al Khafji directly from the PV system, and they don't have battery, but they are, if there is a need, they can take it from the grid, and if there is excess power, they can feed the grid. So this has been proven recently, and they have modified the operation mode several times until they make it operational. Of course, there are a lot of lessons to be learned from this project. In the past, there are a lot of trials in different places in the world, in Jordan, in Australia, Oman, Athens and Canary Islands and Egypt, and all of them either tested in large scale or medium scale or small scales. Now, thinking about wind RO, there are some countries which tried this one, or some locations. For example, in Canary Islands, they have testing this one for relatively medium scale plant. In other location, also they developed this technology in Perth, seawater desalination plants in Germany. Also, they tested this one, and it is the same principle of RO system here, conventional one, just you need power source for this one. For hybrid BVRO, of course, it has been tested in several locations where you need to integrate wind turbine with BV systems. And even here in KFUPM, we have one testing facility, which I'm going to show you the figure of that one later. Now, what are the challenges? I'm giving now the bigger picture. What are the challenges of this technology? In general, there are general challenges. One of them, for example, selection of the geographical location and plant site. Not every site is the best. And when you are close to the coast level, to the coast side, you might have some humidity. You might have some winds which carry with it some salt. So there are some challenges. So selection of renewable energy sources and desalination process, type of feed water intake. This is another one, which is a challenge because as you can see, some technology is better for brackish water or relatively low salty water. We have also another challenge, which is environmental factor. If you are in remote area or in villages, you will have some disposal of brine water. So what will be the solution for this one? So this is another challenge. Other challenge we have, which is very challenging actually, and there are some solution, but we are waiting for a more feasible solution, is the intermittency nature of the power generation of solar systems and wind turbine. And it is considered, at least the capital cost is considered relatively require high investments and financial commitments. So there is a need from the government to support the implementation of this one to scale down the prices. And of course, there is a water crisis in some location or in remote areas and small communities. Now, what could be the specific challenges for Saudi Arabia? We have some challenges in Saudi Arabia. We have many testing facilities, including here in KFUPM, is the dust accumulation. So it will require continuous cleaning of the dust. Some people, they said you can just oversize the system to reduce the impact. Yes, you can oversize it, but sometimes there is a restriction. And of course, this will require some cost increment. Other challenge here is the impact of the temperature. As the temperature increases, as you can see here, as the temperature increases of the cells, the overall the power produced, the efficiency, the health of the system will be impacted to great extent, especially with times. So there are some challenges. Now, is there some solutions? Yes, there are some solutions. For example, is to have hybrid power energy sources, to have more efficient system and advanced distillation technology. And you can have also hybrid system or to be integrated part. When you think about desalination, you shouldn't think about how to do to get the fresh water. You have to think about maybe having pre-treatment, and there is a need for post-treatment too. So you have to think about the complete ecosystem. There are maybe some challenges to introduce some policy and to have also some to develop evaluating and monitoring the performance of renewable energy water desalination industry. And there is, of course, there is a need to have more optimized solution, let me say, the industry, they need more studies so they feel more comfortable. There is reliable solutions. And of course, there has to be control on the demand side. And of course, one of the solutions is to use energy storage, either thermal energy storage, which is relatively cheap, or electricity-based storage, which is expected to be cheap in the future. Of course, in KFUPM, we have really a lot of ongoing projects relevant to desalination, and major part of them is relevant to renewable energy or solar-driven desalination systems. We have conducted more than 46 projects and many thesis work and many publications relevant to water. If we just think about what could be the solutions, is there some samples of these solutions? Yes, there are some samples of this solution. I'm going to explain it based on our status or research here in KFUPM, either from the center here or my colleagues in mechanical department or other departments. So this is one of the experimental setup that we have, which have BV system with tracking option, and it has RO system. So the BV system is integrated with the RO systems, and our colleagues, Dr. Anwar and his teams, they developed smart control system and developed several patents to have more smoothness of to control the RO system. So these are just some of their results, which has been conducted a few years back. And we are working on this one. We are rerunning the labs now with a couple of projects, and our colleagues' work, they were able at that time to get relatively low specific energy consumption as compared to other published work. And they improve the flow by 19%, with optimized tracking BV panel system, and specific energy consumption was around 2 kilowatt per cubic meter for brackish water, which is considered is a good solution. However, still we are working right now to improve these systems. Other work we did it in KFUPM with our colleague in mechanical engineering department is HDH system, and we have conducted at least 10 projects on this technology. Some of them we conducted early stages with MIT, and now we are working also with our team here in KFUPM. We have a really good number of technology, or let me say, a really good number of patents out of this technology, which is HDH. It is quite promising for low or small scale locations or application, as well if you have high brackish level or salty water. It is very promising because you can use polymer based material, and you don't have to worry about scaling or other issues. Of course, there are several patents. One of them is this studies where we were able to integrate many things at the same time, and we got, as compared to the published study, more than 20% efficiency improvement or effectiveness improvement as compared to published studies. So we were able to get really good improvement around 20%. So this is based on solar energy, solar thermal energy, and different mechanism of humidification. The water will be humidified through this water bubble column. Then its temperature will increase, so it has higher capacity to absorb more water. So eventually you can even do 2 stages, and you can get much better performance, or you can humidify the water much better as compared to published study. And of course, the second step is to go and dehumidify it. Of course, our earlier work around 8 years back and 10 years back with MIT, it ended up with some startup company at MIT. And we are happy to contribute at the early stage of the development of this technology. Also, our colleagues in mechanical engineering department, they are working in solar membrane desalination projects, and we achieved some good results. Our colleagues, they are working in this technology for more than 6-7 years, and we are making good progress with several patents and real experimental or real working systems. Of course, in KFUPM, we are happy that to say we are making good advancement in renewable-based desalination systems. We have BV wind RO systems. We have solar thermal systems. We have portable BV RO system. We have solar HDH system, KFUPM Beach. And of course, we were able to do a lot of some feasibility studies to find, for example, the point where we can have achieved no need for BV system. This is just one of the study we did it to optimize the sizing issue of and to have 24-hour smooth operation of BV wind RO system. Of course, in KFUPM, we have a lot of very nice experimental facility. For example, I'll just highlight about some of them. We have solar cells fabrication lab, BV testing, outdoor testing, solar thermal testing facility, desalination facility, outdoor testings, and electrical energy storage. Here in KFUPM, we have really very nice state-of-the-art facility. And we have conducted some work with the University of Stuttgart to develop cooling, solar thermal cooling systems. And of course, we have also some grid integration labs and some facility to test the dust impact on the BV performance. And we have here also our colleague in RI and mechanical engineering department. They have other systems for either solar systems or solar cooling and solar desalination systems. By that, I am done with my presentation, and I'll be glad to take questions.
Thank you. So nice of you, Professor Fahad. You have finished on time. A very nice presentation. This is a very strong step taken for using the non-conventional source of energy for treating the water. There are 3 questions. I would like to sum up 2 questions together just to save the time. First question is about comparison with the different technology. What is the cost comparison related to different technologies for water treatment? And the second question, Professor, is what master track in KFUPM are most related to your area of research? So kindly just respond to these 2 questions, and then I will move to the another 2 questions.
What is the second question?
Okay, first question is about the comparison of the cost of different technology, and second, how your research area related to the different track in KFUPM, master track in KFUPM. Yes. This question okay. Really, I don't, yeah, go ahead.
No problem. Of course, the question about the cost, this slide summarizes the cost based on a published study by Ahmed and his teams in 2019. And it is showing you that in terms of cost, but solar cell doesn't mean it could show it is relatively cheap as compared to other, but still doesn't mean it is practically enough. What I am feeling is, especially in the near future, when we have cheap battery, BVRO will be relatively dominant. So BVRO is very promising for the future. When you think about CSP is also promising. The main issue with CSP, which is based on direct solar radiation, when you locate the CSP close to the seaside, it will be relatively humid. So the air will be full of water vapor. So the performance of CSP is relatively lower than the design performance because it is doesn't receive enough amount of direct solar radiation. So my expectation, BVRO will be very promising in the future. When you think about HDH, where KFUPM is doing well and have some really good advancements, it is promising if you have only in remote areas, or if you have high salty waters.
Okay. Yeah. So the second question was about relating your area of research with the master track in KFUPM. I don't know what exactly mean, but can you answer? Yeah.
We are working in renewable energy in general, either from my background is mechanical engineering. Yeah. This is my strength starting points, and we are working. However, we have very excellent team. We have some group leaders either in the center or mechanical or electrical or chemical or other center in RI. If there is any specific interest, we can communicate and I can connect you with the right person here in KFUPM.
Okay, Professor. So while one of the attendees has praised your very informative presentation, there are two questions quickly I will put together. One question is about, are you aware of any large scale thermal based solar desalination plant? Large scale solar thermal based desalination plant. And second and last question, how I can balance between increasing the efficiency of system and components, complexity of the system. Any balance between the efficiency and complexity. This second question. First question, any awareness about the availability of thermal, large scale thermal based solar desalination? And that's it. These are the last two questions. Yeah.
For the solar thermal plants, large scale, I'm not currently aware of something like this, but I am aware that some countries, they are trying to work in solar desalination. They did some good progress in the past, like Spain, Greece, and as I know, DTRI here in Jubail, they tested solar CSB based desalination systems. For the large scale, I'm not aware of it, but I should mention in Masdar in Abu Dhabi, they have tested 3 technology, which is BV, based on BV and RO, and they started this testing at least 3 or 4. They invited big companies. They have relatively medium scale demonstration level, and there should be excellent outcomes out of that studies. It's worth to take a look to that studies by Masdar.
Okay, so
when you think,
yeah.
So the other question about efficiency and complexity, of course, when you think about, let me say, some technology, I believe it reached to relatively mature level. So maybe you cannot do a lot in terms of thermodynamic or in heat because of obstacles maybe in the material or the technology itself. It is reaching to their theoretical limits. So what the people is trying to do is trying to reduce the waste, trying to have hybrid systems to improve the efficiency, and not necessarily the efficiency to get more water, sometimes to get the wasted heat for other application. And the question is not to add complexity, is to find feasible solution where the industry can pick it from you and apply it in the real world.
Okay. Yes, Professor. So we are actually running out of the time, 15 minutes late, but there is one question quickly. If just this gentleman wants to know about the material which can be used as a medium for humidification and dehumidification process. Just a short answer because we are running out of the time now. Yeah.
Yes. It is air. It is briefly air. Yeah. Air and water. That's it.
Yeah.
You have air and water only.
So nice of you, Professor. Very nice, comprehensive presentation highlighting the water crisis and the remedial measures which we can have, and really fantastic research was presented by you. So inshallah, thank you very much. So nice of you. And we are going to move to the next speaker. The next speaker is also from KFUPM, and he is Professor Fahad Al-Harbi. Professor Fahad Al-Harbi got his PhD degree in electrical engineering with distinction from the University of Colorado at Boulder in 2004. And he did his BS and Master from King Fahd University of Petroleum and Minerals with high honors in 2001 and 1997 respectively. Before joining KFUPM as a faculty, he worked for Saudi Aramco, King Abdulaziz City for Science and Technology, IBM Incorporation, and Hamad bin Khalifa University and its Qatar Energy and Environment Research Institute. Currently, he is a professor in Electrical Engineering Department at King Fahd University of Petroleum and Minerals, and his current research interests are in device physics with emphasis on solar cells, the development and applications of new methods for large-scale atomistic calculations, machine learning, and computational materials design, and multi-objective, multi-scale materials inverse design. Professor Fahad Al-Harbi has published around 127 research articles, and he has 2006 citations and 22 H-index. The title of his presentation is High Throughput Screening of Inorganic Halide Perovskites or Photovoltaic Materials. So, Professor Al-Harbi, you are most welcome, and now you can start your presentation. We are already late by 17 minutes. Inshallah, I hope you would finish in 20 or 25 minutes so that we'll have last 5 minutes for the question and answer. Thank you very much.
Okay,
so nice of you.
I appreciate it. Bismillah ar-Rahman ar-Rahim, and Assalamu alaikum all. First, I would like to thank really the organizing committee for the invitation, and let me get directly to the point. Okay, so what we'll present here is really a kind of a joint work with my colleagues here, Sa'id Al-Qahtani, Abdul Jabbar Sayyid, and myself, and it is for high throughput screening of inorganic halide perovskites. And the outline is we'll start with just general principle for solar cells, then we'll talk about perovskite solar cells, and then we will talk why inorganic halide perovskite, and eventually we'll end up with just presenting some results of the high throughput screening that we have done here for the inorganic halide perovskite. So this is just photos of my colleagues, Sa'id Al-Qahtani, Abdul Jabbar Sayyid, and also some of the work will be presented that has been done with other colleagues like Alam Gable, Ahmed AlSulayman, and Sagir Achkef for the ionic radii estimation using machine learning. And we will present some part of that here, inshallah. So let's start with the solar cell general principle and the current status. In principle, I mean, this is the whole idea of the solar cells, okay? You photoexide carriers, and hopefully we can collect it before we lose the energy completely. And there are two main mechanisms to realize that, either by semiconductor-based solar cell or fast collections. The whole idea that the gained energy, okay, we need to do that either by semiconductor that prevent really the electrons to recombine, or fast collection, hopefully we can get some energy before we lose it completely. The question is, what, from the PHI perspective, what are the needed criteria? From the PHI perspective, we need a suitable energy gap. I'm talking about semiconductor materials here, between 1 and 1.6 electron volt. Also, preferably, we need good absorption and good transport. Mainly, we need the transport length to be much larger than the absorption length. And also we need to the materials to allow convenient band alignment, long-time stability, which is unfortunate with the perovskite. And also there is a need to have low exciton binding energy, hopefully less than the thermal energy. Another aspect, which is environmental aspects, it's the material must be non-toxic and hopefully abundant. This is the famous NREL table for the solar cell technologies and their efficiencies. Currently, it's dominated, if you go to the market, it's by the silicon, okay? And the silicon reached 24% by Martin Green and his team in UNSW in the 60s, or actually in the 1990s. But it didn't improve really that much since then. Currently, the efficiency 26 plus. But the perovskite really, as you can see here, really a kind of a merged recently, and it reached 25% plus. It is expected that the efficiency will saturate, and the issue is not the efficiency anymore, it is the stability. When we go to the market, this is the market share for different technologies, and it is clear, okay, that actually silicon is dominating the market, and actually its dominance is increasing with the time. Like in 2008, it was around 85%, but currently it's 95 plus and growing. And that's it up from the shares for other thin film technologies like cadmium telluride, amorphous silicon, and CIGS, which are, as you can see, are kind of dying when compared to the silicon growth. Hopefully other technologies will emerge that can compete with the silicon, but currently silicon solar cell is dominating the market. Okay, and now when we go to some other device aspect, which is the paradigm between absorption and transport. I mean, commonly, or a lot of people take it's preferably to have a direct band gap material, and this is better. This is just from because the direct gap material provides better absorption, but shorter carrier lifetime, and hence it reduces the transport. The indirect is weak absorption, but the lifetime is getting larger, and that's a kind of equation and trade-off. When we see what's dominating the market, the silicon, it's indirect gap material, it's not direct. So practically, transport properties are extremely sensitive to the growth quality, while the absorption is very tolerable to that. So again, it's a trade-off between the transport and the absorption, and there are a lot of absorbers which has been explored. Over the time. Silicon is definitely number one, but as you can see, there are a lot of materials. If I would like to say like iron pyrite, okay, it has been studied for about 20 years. Unfortunately, there is a very fundamental deep defect issue that prevent such solar cells from really improving in terms of efficiency. But it's very abundant, and the absorption is really good. Just 100 nanometer is the absorption length of the iron pyrite. Now let's go to the second topic, which is the perovskite solar cells. And the perovskite solar cells start actually as a dot or a quantum dot sensitized solar cell. That started with Kojima in 2006, and the efficiency reached about 6.5 in 2011. And then the group in APFL, they introduced the solid whole transport material or medium and the dye-sensitized solar cell. And then that's actually start the plethora of the perovskite work. And then there's a competition between APFL and Oxford, and then Korea get in the business. And the efficiency exceeded 20% in 2015. And now it's above 25%. The question, not anymore the efficiency, it is really the stability. More interestingly, the different device structure has been proposed, either from the planar, mesoscopic, or even ultra thin absorber solar cell. All of them working very fine. Okay, this will tell you how robust really the perovskite in terms of efficiency is. Okay, but there are still three main questions: stability, we have lead, so it's toxic, and device optimization. This is just a glimpse about the publication and the work in the perovskite solar cell since 2012. As you can see, it started with the methylammonium lead iodide shown in blue here, but a lot of work had followed, okay? And it's recently the lead-based perovskite really start getting in business. Currently, the efficiency for the cesium-based cesium lead iodide is around 18%. And as for the efficiency, it started growing really fast, but we are expecting really that we will reach a saturation, because actually the thermal limit is around 29%. So the improvement in terms of efficiency will be limited. The main remaining question is the stability. Saying that as well, this is just a kind of the number of publications published in perovskite. And as we can see that it's exponential growth. But let's look at the interest of the publications. Initially, to 2013 and 16, efficiency was the main driver, which is shown in black here. But since 2016 and on, okay, the stability is the real concern, okay? we will expect actually the efficiency will saturate, and in terms of publications, more work will be directed toward the stability. Okay, so what is really the main issue of the stability for the perovskite? Unfortunately, there are tons of problems there, some of them extrinsic and some of them intrinsic. I think Naziruddin talked about some of the extrinsic, like the UV degradation and the titania, and also the whole transport material, but I'll focus about the intrinsic. Unfortunately, okay, the methyl ammonium lead iodide is intrinsically unstable. Okay, if given enough time, it will decompose. And that actually has been shown experimentally and also computationally. When we go to the potential of the solar, I mean the perovskite solar cell, I'm talking about the methyl ammonium lead iodide solar cell. Okay, there are three, or the triangle corners for the application of the solar cells. It is the cost, efficiency, and lifetime. In terms of the cost, definitely the perovskite is cheaper than silicon. In terms of efficiency, they are comparable. The main issue, as you can see here, is the lifetime. The silicon give you 25 plus years. The silicon is much less than 1 year. Okay, so if the perovskite to hit the market, it should really a kind of improve in this category. Saying that, there has been a lot of work really to improve and to stabilize the perovskite. And most of the work was tailored toward really the methyl ammonium replacement. And there has been a lot of work. And if we just look at this figure over here, let's look for the 1000 plus. Most of these material, these figures are not anymore three-dimensional perovskite. They are actually two-dimensional perovskite. And with that, there is additional device problem. Preferably, we prefer that the electronic transport to be three-dimensional. By reducing the electronic transport dimensionality, that will make additional challenges from device perspective, not material perspective, for the operation of the solar cell. We have to make sure that the transport is going in the direction where it will be collected. Now let me go to the third part of the talk, which is regarding the why inorganic halides. As we said, the methyl ammonium lead iodide, it's intrinsically unstable, and there are a lot of work showing that, both computationally as shown here by us and other teams as well. And there was actually also experimental proof for that. This is a direct calorimetric verification of the thermodynamic instability of the perovskite. And as we can see here, this is for the enthalpy of formation. The deeper it go, okay, the stabler it is. As you can see here, MAPI is actually unstable, just from the enthalpy of formation. Give it enough time, it will decompose. Okay, as a pure phase methyl ammonium lead iodide. And if we go for actually down in the group, we find that actually going up in the group, actually we can get more stabilized system, like going from the iodide to bromide to chloride. But unfortunately, if you go up in the group, we change the optical properties. It's not stable, suitable anymore for solar cells. For example, the bromide, it's getting to something like 1.92 electron volt, which is a bit outside the range suitable for solar cells. Another thing about the stability, the people tried many things, and different humidity level, different transport materials, and everything, as you can see here, actually end up that in a reduced or that the stability is actually just measured in hours, not days or even years. It's unstable. Okay, saying that, actually, as we said, we believe that actually it's intrinsically a main problem. It's in the structure. The methyl ammonium is not contributing to the valence state of at the top of the valence state valence band. That's why it's actually just a structural contribution. It's not electronically connected to the octahedral framework. Let me now go to why inorganic perovskite. Could be when we go from the organic cation to inorganic, hopefully that will make the material more stable. Also, we can have a reasonably large material space. It's 9,000 combination if we consider the uncommon oxidation state. And a lot of the knowledge known for the methyl ammonium lead iodide can be transferred over there. Okay, this has been suggested actually by many, and I'm just showing here like the paper by that's from also Australia, and untapped potential of inorganic metal halide perovskite. And just to show the potential, this is the cesium lead iodide, and it's already the people realized 18% efficiency last year. So there is really a good potential for a pure inorganic halide perovskite. From just a kind of energy landscape, we can see that actually the halide perovskite provide actually a small landscape when you compare it to the chalcogenide or oxides. Why we focus on them, while the oxide are much more stable than the halide perovskite. The issue for there is the suitability in terms of energy gap. And there are a lot of work, but we will, on the oxide and chalcogenide, perovskite, but we'll focus here just on the halides. I'm coming now to the last part of the talk, which is the high throughput screening for inorganic halide perovskite. So the approach that we do present here, when you go to computational material design, either you go by material by inverse design or backward design, as we call it, or the conventional approach, which is the forward screening, and that's what we are presenting here. One of them is just function by design. That's when we go from really, inverse design, but the approach we have here is really forward screening. So how we do that? We need to identify the possible elemental set for the AP when we talk about APX3 perovskite. Then we generate the screening material space, and after that, we need to start from some point for the initial guess. We need to approximate efficiently the high symmetric phase structure, which is the cubic. After that, we go for a global type of optimization to identify, hopefully, the global minima. Hopefully, we never actually know exactly if this is the global minima. And after that, we calculate the band structure using GW, not DFT. Let me start with the structure. This is the structure of the perovskite, which is the APX. And these are the combination. We need the A to P plus 1 cation with a 12-fold coordination. The P is a plus 2 oxidation state with 6-fold coordination. X is the halide, obviously, with the -1. When we consider only the common oxidation state, this is actually the materials that we could, or the element that we consider in our screening. The green one showing the A, and the orange is for the P site. Obviously, the highlights are the X site. And out of these, we can manage to get like 576 possible compounds. This is just for the common oxidation state. But why we limit ourselves? It's a computational work. So why we don't go for even the uncommon oxidation state? And with that, we end up with more than 9,000 possibilities. And this table showing actually the combination we have. The green is a pure A possible sites, and that's obviously in the alkalides. For the remaining blue, it can be played as A or B. If we consider, we said here, the uncommon oxidation state. So it can be in the A site or the B site. By considering that, we end up with 9,592 possible materials. Okay, now we go to some details for the calculations. For structural geometry, obviously, we can rely on DFT GJA. It's the approximation is, the accuracy is more than 3%, so it is really good. But we are left with some questions. What should be the initial guess? Okay, we don't know most of these materials. This is our hypothetical material. So we need to start from some point with the initial guess. Second, what are the optimum optical and physical parameters for the calculation? Third, what are the minimum number of atomic sites to use to allow the possible perovskite phases? Third, for the optimization, we are looking for the global minima. So we need some global optimization scheme. For the possible, perovskite phase, there is no single actually space group for the perovskite. There are actually 23. And here, let me use the Glaser table for the perovskite. And these are, all of them are perovskite structures, okay? But obviously, you start going from the cubic phase to trigonal or others by changing the APC or the angles, then we have a different space group. But all of them are perovskite structures. What's really important here is this. To be able to capture most of them, we need to go for 2 by 2 by 2 atoms. What does that mean? That we need 40 atomic sites to really capture the global minima for any of these perovskite phases, or even probably not perovskite. and we shouldn't apply any geometric constraint. The optimization must be free in volume and atomic positions. And if we start from cubic phase, we end up with a problem because the cubic phase is actually a proper local minima. So we need to hop out of the cubic phase. So for the global optimization, there are different ways. Either we go for the genuine global optimization, and there are two softwares for that, Calypso and Osbech. But another alternative way is to go for random sampling with the gradient optimization. And this is actually what we opted to do. So we went with random sampling, but with our modified version. So we start with the initial structure, then we randomize all the atomic positions with distortion, and we build about 10 initial guesses, and then we go with the gradient optimization. Another thing, which is if we are looking for that, we need to have a good initial guess, and the one that will determine really the proper initial guess is mainly the bonding distance, which is associated with the ionic radii. The main source for that is Shannon table, and Shannon table shown here. And it's actually maintained, the data is maintained by Imperial College. They tabulated experimentally obtained ionic radii for different combination of oxidation state and coordination number, like 480 possibilities. But that's not enough. There are more than 1,000 possibilities. So for that, we applied machine learning, prediction or regression model to predict the atomic radii or the ionic radii from the coordination, oxidation, orbitals, and the period. And the work is actually in process of the publication, and we get the accuracy of less than 3 picometer in terms of predicting the ionic radii. And we use this in our calculation, and just to show how that's implemented, I will skip this. By the way, our model is already in the net. If somebody is interested, you can go there and apply it. This is just when we implement it for our work here. So based on the ionic radii we obtained, we put the initial guesses, and this is our initial guesses for the cubic phase. And after we optimize the initial, just the cubic phase, this is the optimized value. And as you can see here, the error in many cases is less than 1%. Actually, the mean for the error is about 2%, and in many cases we just hit almost the optimized lattice parameter just using the machine learned ionic radii model that we developed. Another important aspect, which is for each element, there is a special set of optimal numerical and physical parameters. In a single APX, there are 3 compounds. So, and each, or 3 elements. So each element will have its optimized parameter, which one to use. Okay. Also, when we go to the high throughput, we will have thousands of possibilities. How can we cover all of them? There are 3 possibilities. One, to use a standard set of parameters. Unfortunately saying that, this is very common. The second, use extreme set of parameters, but that's computationally very expensive. The third, which is really developed by the AFLU team, and they put it in materials cloud, they developed what we call it the standard solid state pseudopotential. And the idea there, for each element, okay, there will be a set of possibilities. And the one here, it's the what is the best pseudopotential to use, what should be the cutoff for the wave function, and what should be the cutoff energy for the charge density calculations. And we use this in our calculations. And just to show why these are really important, this is just for the the cesium lead chloride. Okay, if we use different cutoff, okay, and the standard value is used between 30 and 40 Rydberg, but actually we don't reach a convergence till we get something like 50 and 60. So it's not, really a kind of just plug and play. The best optimal parameters must be used. Our work has been automated, and the calculations are in progress. I should have said that we are using, thanks to KAUST, the KAUST Shaheen system. And this is just a small subset for illustration here, where we use for the A site potassium, rubidium, and cesium. For the P site, we use lead and tin. And for the halogen, we use chloride, bromide, bromine, and iodine. And the work is actually, hopefully soon will appear, inshallah. And this is the title of the work over there. And we use this just to tune the probably the random sampling parameters and to have a comparison with highly accurate reported work. So just for the random sampling to show that we reach, hopefully the global, I'm not really sure, but we reach really very high, very strong minima by when we go for 10 samples, for example, here for the chlorides, we can see that we get actually two minimas. One, which is a bit shallow, but this is really deep. And all the 9 of the random samples we use reach that minima. When we go, for example, for the cesium, we have actually 3, okay? But only 2 of our random samples really reach the minima. And we do actually further investigation for that to make sure that we really reach a very stable phase. And this is applicable for all of them. And just for the finding, the distortion more than 15% result in the divergence. 10 random samples should be enough actually, but we need to hop away from the cubic phase. This is just the result to present. This is showing the calculation in blue by our work, and Shijan and Yen, they're trying to determine what are the most stable perovskite phase for the same set of elements that we are using here. And they were focusing in the perovskite, but in our calculation, we let everything free. So sometimes, probably in some cases, we end up with non-perovskite cases. Actually, we found that for the lead, we end up with the perovskite, but for the tin, definitely we are not anymore in the perovskite phase, but actually it is pyroxene phases. And this is just a list of the calculation. Here we show some, just one example for highly tilted perovskite, but still perovskite, while this one here is a pyroxene shape. With that, I end up with the presentation. Hopefully I didn't take more time than needed. Sorry, Shamsad, for that.
Thank you. So nice of you, Professor. Very nice presentation relating the material and energy with very high level analytical approach. In fact, there is not big, so many questions. You have a praising from Professor Gundal for a very nice presentation. There is one question we can take up at the end because we are running out of the time. So if you allow, I can move to the next speaker. Our next speaker is Professor Ibrahim Dinser from Ontario Technical University, Canada. Professor Ibrahim Dinser is known to KFUPM. He was faculty here a long time before. And he is recognized for his pioneer works in the area of sustainable energy technologies, and he has co-authored numerous books and book chapters and many refereed journals and conference papers. He has chaired many national and international conferences, symposia, workshop, and technical meetings. He has delivered many keynote and invited lectures. He is an active member of various international scientific organizations, and he has served as editor-in-chief, associate editor, regional editor, and editorial board member on various prestigious international journals. He is a recipient of several research, teaching, and service awards, including the Premier Research Excellence Award in Ontario, Canada. During the past 6 years, he has been recognized by Thomson Reuters as one of the most influential scientific minds in engineering and one of the most highly cited researchers. Professor Ibrahim has 1,602 articles published according to the Google Scholar records, and he has a total citations of 60,625 with H index of 115. So nice to see such a great personality in this area. Professor Ibrahim, kindly proceed. Thank you very much.
Yes, thank you. I will now share. Is it seen on your side?
Very clear. Proceed,
Okay,
Professor.
Excellent. Thank you for inviting me for this unique event, and I will be delighted to share my thoughts about really hydrogen technologies. And the title is a little bit controversial, but sort of a reality. And everything is really coming out of my article. This was a sort of a perspective article when I started writing it back in April, let's say mid-April. And really what I have seen, humanity needs clean air, clean water, clean food. And when I look at the overall picture, really energy was playing a critical role. And clean energy has been essential. So I was really trying to formulate this. So we have been in a carbon age up until this, and then now we gotta move into hydrogen age. So this was sort of, when you look at overall, air pollution and other issues overall globally and locally, so ending up with many health-related concerns. So making us really focus on hydrogen and really try to decrease carbon contribution. And this was a whole point. And then also, I got funding, industrial funding for one specific project. And this specific project was about really to bring something into the picture here, trying to combine, what we need. We need hydrogen, we need oxygen. So hydrogen, clean hydrogen is really essential. So on the other hand, we have oxygen, produced. So why not supplying it to really for COVID patients, for example? So that was another point. So I have one unique project related to this. So bringing it down and making this in a way, really hydrogen production is important, and through water dissociation. So that was another important thing to highlight in here. So in my lab, I have been really leading various projects and technologies, hydrogen and fuel cell technologies, renewable energy technologies, energy storage, advanced power generation, hybrid and electric vehicles, alternative fuels and production technologies. So these have become sort of my really projects portfolio. And dealing actually with these with a large group. So that is my advantage. Also, one important thing before I get into the specific subject, and this is very important, research, innovation, and commercialization. In the morning, we had, of course, some key speakers dwelling on, and it is really important. Same thing goes for me. Turning knowledge into technologies is very critical. So that's why in my lab, at the end of the day, really we try to turn the knowledge developed into technological products. When we look at the energy picture, energy picture is coming down to 3S: source, system, and service. Source, you need a source anyway. So what sources we have got? We may have basically fossil fuels, we may have renewables, we may have nuclear, or maybe other some waste or process heat, whatever is available. So that's why we need to be recovering. And then at the same time, we need to produce some useful outputs. I see them like services under S, and these useful outputs will be necessary, such as power, heat, cooling, fresh water, etc. So, and then what happens now, the equation is coming down, and we have a source, we have services needed. So is it possible to drive the equation into to design my integrated system? So making it that way. At the same time, there is another S coming into the picture. Imagine between source and system, such as solar, and the sun is not shining all the time, wind is not blowing all the time, you need a storage. So another S is coming into the picture. So what if the system produces more than what you need? So another S is gonna come into the picture. So storage will be again in this equation. So what you do overall when you look at this, 3S plus 2S will be really essential to solve this sustainability equation. And then to look at the dimensions of sustainability, is it really only coming down to energy? No, we have 4 more E's. We have education, we have economy, we have environment, we have ethics. Some may question where is the social dimension. I really take this social dimension into ethics. Ethics is a kind of larger spectrum. You know, when you cover that, you cover social dimensions as well. So this is going to be necessary to be able to provide overall sustainability. And then the key targets, when we look at overall, you know, what targets we should have in mind, and these are gonna come down to better efficiency, better resources use, better cost effectiveness, better environment, better energy security, better management. So these are going to be able to achieve better sustainability. So now we are, of course, having this in mind, and then to look at the useful outputs. So what we need at the end of the day, useful outputs. So power, heat, cooling, fuels, fresh water, and others. So now we have these useful outputs needed by the users or communities or the society at large. I have to make the case by looking at the history of fuels. And when you look at the carbon-hydrogen ratio, what you see here, humankind started with wood, later coal, oil, natural gas, and what you see here, carbon-hydrogen ratio is going down. So now, this is clearly addressing that in line with what I have said a little earlier. So making it really getting into hydrogen economy. So you see, it is obvious we are now making this. And this is really where I have described this COVID-19, the pandemic, a kind of turning point. When we look at the transportation sector, so every vehicle is crying, and what they really need clean fuels. So really, that is something we need to see. Okay, what about the world? And the world, as you see here, suffering and really needs solutions. And we need to cure this, and really hydrogen is coming out as a key solution. But one thing in mind, you know, hydrogen, you know, most of the people see hydrogen as an energy carrier. So yes, but there are 2 more items to consider. One is you know, using it as fuel, but more importantly, as a feedstock. I will mention a little later why it is becoming more critical. When you look at overall, you know, what has been going on around the globe, in January 2017, they formed, you know, 13 global industry leaders formed the Hydrogen Council during the Davos Economic Forum. So at that time, they had 13 members, but now they have got over 90 members, really trying to come up with the hydrogen economy related solutions to faster this and really combat actually global warming issues. Several countries started developing their roadmaps in this regard. You know, one example from Japan. Look, started holding the hydrogen energy ministerial meeting, started in October 2018. They did last year in Tokyo again in September 2019. And look what they have come up. You know, this is specific to Japan. And really in 10 years, 10 million hydrogen power systems and 10,000 hydrogen refueling stations. You know, this is just in Japan. And then this year, they had another follow-up meeting. So making it this way and really developing the platform at the ministerial level. So to really expedite the switch to hydrogen economy. Europe started this way with their Clean Hydrogen Alliance in past July. And then also they have started developing sort of sector analyses and to look at really what will happen during the pandemic and after the pandemic. And then also, of course, countries started their actually declaring their plans for the hydrogen economy, developing their, let's say, cities in a more, let's say, in a more sustainable manner. And this is one of them from Germany, really dwelling on green hydrogen. China is proceeding that way. And in Canada, yes, it has been very critical. Canada has been at the forefront, and the hydrogen strategy, this is just a new document. And it was a draft, so the actual document came out just last week. And when you look at oil companies, and this morning also, it was nice to hear from the Aramco rep talking about, you know, these green solutions. And look over here, this is one oil company really focusing on hydrogen and renewables. And look at this, actually another oil company. Basically, it was British Petroleum, but now it is Beyond Petroleum. So they kept the acronyms, but you know, when you look at it, it is beyond the actual petroleum. So basically, the main focus you see here, hydrogen. And they know hydrogen is the main feedstock and fuel. And so it is really essential to dwell on this, produce it in a clean manner. But when you look at the perspective, overall, the picture related to hydrogen production, only very small percentage, look at here, using actually electrolysis, only 4%. And when you look at it, how much percent is clean? In the early 2000, it was less than 1%. And in 2019, increased a little bit, but it is not really with clean electricity. Only 1.3% is clean electricity. When we look at this, this is by our works to look at the entire life cycle assessment. And in terms of hydrogen production methods, so is it really meaningful to use fossil fuels for hydrogen production? And this is showing that is not. You may be able to reduce the emissions a little bit, but in general, when you look at the perspective, is not really helping out. So what does it mean here? And when you look at here, the key is going to be really to focus on renewables and nuclear in terms of hydrogen production, and basically trying to dissociate water into hydrogen and oxygen. and doing one perspective article to look at overall in a Canadian setting, to be able to see the research and development efforts related to different hydrogen energy related technologies. And this is just to show that, you know, how many publications during or since in 1970s came out, and my university is leading. And really, my group is the leader in my university, basically, even in Canada. And so these are the really points to make. Now, getting into the research I have been doing actually with my group. Really, the first part is going to be about thermochemical or hybrid hydrogen production. And this is coming down to basically thermochemical and hybrid cycles. And initially, of course, as a large group, so started dwelling on copper chlorine cycle. And we also developed an integrated cycle, and its prototype was built in our clean energy research lab. And then getting into magnesium chlorine cycle, that is also being developed. Even there was initially a 3-step, and then we developed a 4-step cycle, and to make it more viable, really at the commercial level. And then getting into hybrid sulfur and also integrated systems to be able to really incorporate this thermochemical cycle into the energy systems, particularly with renewables, and to be able to produce multiple useful outputs. And then another dimension, and to be able to look at the photonic hydrogen production. And of course, doing PV electrolysis, photoelectrolysis, photocatalysis, photoelectrochemical processes, and also moving into integrated system. And I have had a couple of projects, and I have also a meeting today with my European partners that was really about using wastewaters for hydrogen and clean water production. And also at the same time, producing chlorine for commercial purposes. So you see this way, and ending up with integrated systems, trying to bring multiple dimensions into this and really overcome multiple issues, and to be able to provide multiple useful outputs. And then also getting into another project, and I have had also one of my Saudi students working on high temperature solid oxide electrolyzer, and for hydrogen production. That was also another successful project. And then also to look at the steam based hydrogen production, of course, through microwaves. And that was also another successful project completed. You know, this was also with another industrial partner, to be able to check the really the feasibility of the process. And then getting into another one, this was aluminum and the water chemical reactions. That there was another industrial partner, really coming to me and really asking for this process to be able to really investigate, and that was another work done. And also at the same time, developing technologies and moving into another dimension, because when you have a hydrogen in hand, what you can do, you can move into other solutions. And this ammonia, and I have been working and I have been leading various projects in this, really to make a kind of shortcut solution. Shortcut solution by using ammonia for various purposes. Ammonia can serve as a working fluid, as a refrigerant, as a fuel, as also a hydrogen storage medium. And what you can do, because it is NH3, and I will be showing another technology this way, but this particular one, and this was actually, again, I had an industrial partner coming to me and asking for this kind of fridge size ammonia generator. So using clean electricity and water, air, and producing ammonia. That was a whole point and successfully completed. Now it is being actually patented. And also gone into, of course, in the past, my group did various works on PEM. But since started working with ammonia and wanted to diversify this fuel cell research, really getting into electrolyte-based direct ammonia fuel cells, and published multiple papers. And this was also another important subject. And really, this technology is also being commercialized. And since bringing the solutions with ammonia, to look at also solutions particularly for transportation sector. And for the vehicles to be able to use ammonia fueled internal combustion engine, ammonia decomposition and separation unit, and also a fuel cell system that way. So bringing all these technologies, these are also being commercialized. So we have industrial partners for this. So these are some recent works. And also in ammonia production, we studied the effect of electrochemical magnetic field and whether or not this is going to help increase the efficiency. So what we have observed that, 3 to 4%, depending on the conditions, to be able to improve the efficiencies. So that was quite interesting, and we published some of them. And that was another interesting publication. This was actually some years ago. And when when an automaker came to me and asked for for a kind of alternative solution, and instead of doing storage on board, and asking me if we can find something really game changing. So at that time, my thinking was, why not changing the game here? Instead of going with hydrogen, why not going with ammonia? And the technology at that time developed. It is now being commercialized by hydrofuel. And why not doing the following? So filling the tank with ammonia, and we have the technology in terms of ammonia decomposition and separation unit on board, and really separate ammonia into hydrogen and nitrogen, and using hydrogen either directly in internal combustion engine, of course, after making the necessary modifications, or in a fuel cell system, and then nitrogen for cooling purposes, and even helping for NOx reduction. So when you look at this was an interesting project. And then more recently, I have been leading some projects related to renewable hydrogen for natural gas. And I am leading one project in Turkey. And this particular project is related to the following. Really producing hydrogen by using renewables, and also doing the following, because to be able to improve the combustion performance of natural gas, and also improve the environmental performance by reducing the emissions. So this was a particular study, and completed the prototype successfully. Now we are moving into next level to do a pilot study with a building or industrial facility. So this is why this is important. When you look at it overall worldwide, from North America to Far East, especially in Europe, in several countries from Germany to UK, and they are trying to really reduce the carbon footprint by blending hydrogen into natural gas. And that was a whole point, to be able to blend with renewable hydrogen up to 20% by volume, and to be able to, of course, increase the efficiency, combustion efficiency, and also reduce the CO2 emissions. And then also the system, of course, developed and finalized. Some specific details are given here, but it is also a niche technology. This particular one is also being patented. In Oshoba, I have a partnership with CC Solutions to develop a hydrogen hub. Hydrogen hub in basically in Oshawa, and the aim is the following. So to be able to utilize the sources such as nuclear, renewables, and these are what we have got there. Nuclear, we have Pickering Nuclear Power Plant, Darlington Nuclear Power Plant. We have solar, biomass, wind, and hydro. So the key approach here, we have technologies being developed, 3-step copper chlorine cycle, 4-step, 5-step, high temperature electrolysis, conventional electrolysis, photocatalysis, photoelectrochemical or photoelectric catalysis, photoelectrochemical processes. And now, even additionally, to look at the options to be able to feed a transportation sector and other economic sectors, really with this. And the key started with the transportation sector. So, and I have got some funding from the transportation ministry, and trying to develop this hydrogen hub, basically hydrogen hub, and then also bring industrial partners, and really extend this for the province. So obvious, of course, point to make here, renewables will better survive with the hydrogen energy solutions. And then in here, of course, what we do instead of doing storage, especially when we have wind, so why don't we do really this using electrolysis, and really produce hydrogen and store it and use it later when needed. And also, again, going one more step ahead to look at this. So again, ammonia research has become more and more important Why? Because of the infrastructural requirement, especially when you deal with hydrogen. So what you can do, you can move one step ahead and synthesize into ammonia and take ammonia and bring anywhere. So easy to store, easy to transport, easy to actually manage in many ways. So what you can do later, you can use based on the technology we developed, dissociate into or separate into hydrogen and nitrogen, or use ammonia directly. I can tell you one example. And I have been working with these technologies. Even Toyota came to my lab, visited, and then after that, they started working on ammonia technologies. Japan initiated a new program in 2017 on ammonia, specifically on ammonia, and trying to develop ammonia gas turbines because NH3, it is carbon free. The question, are there any challenges? And I always tell people, energy solutions are like drugs. Do you know any drug with no side effect? I know none. So every energy solution has some side effects. So this is a reality. So that's why, every day you hear, oh, this solution is completely clean, no side effects. No, don't buy that. In every energy solution is like a drug and has some side effects. So the key is the following. When you go out, what you do when you have a patient, you try to find the right expert, right doctor, and get the right prescription for cure. So you really want an expert to diagnose the problem. So similarly now, when you deal with energy, accordingly, you need to come up with the right prescription. This is very critical. Right energy prescription is essential. And then ammonia. And this particular one, and basically for transportation sector, look at overall, and this was really trying to come up this map, and especially in terms of volumetric energy densities, specific energy densities at the shaft. And when you look at overall here, by using ammonia, ammonia is a hydrogen storage medium. And what you can do, you can also use ammonia directly. So, and I have got multiple projects really trying to convert gasoline and diesel power generators to run with ammonia. Yes, of course, there are issues such as higher auto-ignition temperature, slow some chemical kinetics, and then low flame speed and that kind of stuff. But we are developing the technologies and to overcome such issues. And that's why in addition to hydrogen, and then I was really proposing a kind of a solution with ammonia, going together, and basically to be able to, produce ammonia and supply to various sectors. But the key in here, when you look at this, we need renewables, we need hydrogen production solutions. Hydrogen production solutions, of course, it can be, as mentioned earlier, using some or one of those technologies. So what you do, you will synthesize into ammonia and then supply to various sectors. So these are sort of trying to come up with the ammonia economy. This is very interesting, and I have a perspective article about this. You know, it is gonna be coming out soon. How to overcome ammonia combustion issues, and trying at the same time provide a perspective about the ammonia-based economic cycle. Ammonia-based economic cycle, again here, and when you have renewables, and what you can do, you can move and produce hydrogen, and then also you separate nitrogen from air and synthesize into ammonia, and you see, you can supply to various sectors. And that's why it is going to be even more critical. Look at, you know, in how many places we can use it. We can use it as hydrogen carrier, in power generators, fuel cells, cleaning agents, energy production, as refrigerant, fertilizer, feedstock, and chemicals, using it even in engines, you know. And when you look at the diversity is huge. And this is also another important solution. So the point here, and yes, hydrogen economy is essential, but hydrogen is going to be at the same time serving as a main feedstock. And what you can do, you go one more step ahead and deal with this and into ammonia. And also the other important thing, I'm also watching the time. And the other important thing, enhancing the research, especially when you have renewables. What you can do, you produce hydrogen, and then what you can do, you separate air from actual air to get nitrogen and synthesize into ammonia, carbon monoxide into, of course, hydrogen, and carbon monoxide into methane, and then with again into methanol, ethanol, dimethyl ether, and these are becoming sort of renewable fuels or synthetic fuels as part of this hydrogen-based economy. And then really what you can do, fit really into the sectors, economic sectors you have got. And from transportation to industrial, utility to agriculture. So becoming very important. And also, of course, at the same time, bringing solutions by incorporating our developed cycles, hydrogen production into various systems, and this is one of them, and incorporating it into this kind of solar energy based or CSP based system, and of course for multiple outputs. And also doing, of course, solar biomass based systems. And this is one of them, and really trying to produce multiple useful outputs. And this is another integrated system. To look at also industrial heat recovery options. And I did comprehensive work for various industries, especially when we look at the high temperature needing industries, from steel making to glass, cement, and all those things. We have really high temperature level heat available, and to be able to use for various purposes, and this is one of them. And then also to look at renewable methanol, and we have actually carbon dioxide, because what we know, oceans absorb carbon dioxide. So the key solution was, this was another interesting project did. So is it possible to come up with a district energy system where we can have multiple useful outputs. This is just one of those systems. And you, of course, generating power, heat, cooling, etc. Even in this particular case, methanol, and we have an interesting electrolytic cation exchange membrane is ICM reactor incorporated into, and then making this renewable fuel. And this has also been published. And then also looked at various other potential options. And you basically targeting to produce dimethyl ether. And this was one of the actually here using renewable energy based solutions. And this way to be able to develop these technologies. And these technologies technically and DME and power accordingly, this is solar based. And also we have, of course, carbon dioxide captured and used accordingly in this cycle. And also another one here, adding also another useful output, fresh water into. And this was another interesting study. All these three systems have been published, and very interestingly bringing these solutions and to be able to really bring the solutions in a way where we can get renewable fuel in addition to other useful outputs needed. This is something, you know, you may be thirsty by this, and look at here, very interesting. And I was telling people, you see now, if you want to make money and be rich, and this is one option. So now what happened? And from Japan to Europe, there have been initiatives, you know, really to bringing up the hydrogen drinks instead of carbonated. Now this is really with the hydrogen. And also there is a medical article published and trying to show what benefits hydrogen is gonna be really providing. So very interesting, you know, and this is something I haven't done any research, by the way, so this is not my area. So I am just giving you something, you know, and to be able to see even going down to the drinks. And yes, very interesting. So the bottom line, hydrogen is not the end. Hydrogen is the just the beginning. So really, when you look at here, hydrogen is going to be serving as energy carrier, fuel, and feedstock. So I stop here and entertain.
Thank you, Professor Ibrahim, for finishing on the right time. So nice of you. Wallahi, highly impressed with your very comprehensive and starting from scratch to the highest possible level. You have explained everything in a very clear manner. And I actually 12 people have put their comments, but out of 12, 9 are just appreciating you. Okay, there is no question. Just they are praising your effort, and you know, we are very glad to have you here. And I know you are working as associate editor for our AJSC journal, yes, Arabian Journal for Science and Engineering, and there your contribution is really very significant. And we hope that
one of the former KFUPM employees.
Yes, I told in the beginning, and we would like to take advantage of your all these achievements. Inshallah, God willing, we might collaborate. The people working in this area might collaborate with you for starting here in some area of hydrogen.
In this regard, you know, and I have no issues, and I am open to that. Yeah. So this is something really important. I am not saying hydrogen is going to be the only solution. No,
Yes,
really,
yes.
we need to diversify this. And hydrogen economy is going to be a reality. So,
Exactly.
and that's why we need to be ready for it.
Yeah.
And daily is going to be changed. And it is being changed, by the way. And
Yes.
when you look at these oil companies, so really every country needs to act very quickly. And that's why when you look at here, hydrogen it shouldn't be seen only as a fuel, no, energy carrier, no, not only that, but more importantly, key feedstock. So that is very critical.
Yeah. So some just quick question, Professor. Just one couple of questions we can take. One question is about the limitation of using hydrogen energy in cars. Only Japan has adopted and the gentleman wants to know and he wants your comment about why the hydrogen energy lost the competition with electric cars.
Okay, this is, you see, always I see this question is something very common. And when you look at this, you know, I don't say hydrogen is better. You know, when you look at it, by the way, hydrogen vehicle did better than Tesla electric vehicle, by the way, when they were rallying. So it was, I think, last year or last summer. So last summer, I guess. And but this doesn't mean that, you know, hydrogen is better than electric vehicle, or no. There are cases hydrogen is better, but there are cases, of course, electric vehicle is better. But when I look at this, I see on every side we have issues. We have issues related to hydrogen. We have issues related to, for example, electric vehicles, especially coming down to battery thermal management. We haven't really solved all these issues. Imagine when you have an electric car, let's say a Tesla electric car, you have over 3,600, you know, those little batteries. Imagine, you know, if something, you know, happens to one of them, you know, the performance is gonna decay. So when you look at overall performance, basically thermal management issues, other things, and so on and so forth, requiring clean electricity as well. You know, this is also, what I am saying, we don't need to select hydrogen over electric. No, what I am saying, each solution has its own issues. We need to accept the reality. That's why I said, you know, energy solutions are like drugs. Every drug has some side effects. And that's why, for example, if you have two patients complaining from the same disease, going to the same doctor, ending up with two different prescriptions. Why? Because one may be allergic to something. One may have issues internally, you know, may not be suitable to take, let's say, certain specific cure or treatment. So it is always necessary to look at the really 3S picture. And 3S picture is very clear. In the beginning, I wanted to provide that, you know, source, system, service. You need to look at what sources you have got and what useful outputs you need. And then what you need to develop your systems accordingly.
Yeah. So,
And
Professor,
this is going to
there,
be coming down to your infrastructure as well.
Exactly. So there is another similar question, and one professor from KFUPM, he's asking about the risk of ammonia, and if you are putting in a car and there's a risk, and it is a toxic material, is it safe to transport and store as compared to hydrogen? This is one question, and the last question I would like to sum up so that you can answer simultaneously.
Okay.
Another question is that he's asking, kindly give comment on the use of microwaves in generating hydrogen, and if that method efficiency is compared to the conventional use method. So these are the two concerns, and that's it. One is related to risk associated with ammonia.
Okay, yeah,
Another
basically ammonia safety. You know, when you look at ammonia, there are two issues, toxicity and flammability. And this is basically coming down to excessive amounts. And especially when you look at many other chemicals have even higher rate of toxicity. So, of course, in this particular case, even what happened, and there is ammonia forms really developed in this regard, solid ammonia, and for these purposes. But when you develop, imagine when you have hydrogen at 700 bar, and nitrogen, you can make it basically better and much safer. And that is possible. Only excessive amounts, yes, causing problems, but even in various amounts or levels available in many things, And those ammonia is not new in refrigeration sector, has been used for so many years, even before CFCs actually got into. We had ammonia being used household fridges. There is no any single fatal event reported. So when you look at every chemical has some safety concerns, and I accept, and ammonia has, yes, I accept. So just like other chemicals. And then coming down to the really this microwave-based hydrogen production.
Exactly.
Yes, it is, yeah, the efficiencies will be low, because especially high energy density is needed, because you are talking about microwave, and then now trying to separate. And of course, what is most efficient, really electrolysis. And then even in thermochemical cycles, depending on the cycle you choose, so efficiency is going to be from 20 to 40%. And depending on the integration you do and depending on the heat recovery you manage. But overall, really, the efficiency here is very low.
So thank you, Professor. So nice of
You're
you.
welcome.
Yes, out of 14 comments, 10 are appreciation for you. We hope, inshallah, we will again invite you for another occasion, and we hope your very strong association with our AJSC journal, which is booming now, alhamdulillah, going up in citations and the impact factor, and we will associate with you for research collaboration. Thank you very much. So nice of you, Prof.
Thank you, and all the best. Have a great day.
Yeah,
Bye-bye.
thank you. So nice of you.
Bye.
Okay. So I would like, okay. Here we are still waiting for our last speaker to join us. I don't know if, because it is now 15 minutes past the scheduled time, even more than that. So he is not around. So what to do, Professor Muhammad? Yeah.
Assalamu alaikum. Yes, originally, because he mentioned that he was going to join early, I don't know what happened, frankly. I tried to reach him. I could not. I asked around people who have his mobile number. We don't have his mobile number. We just have his office number. So what I suggest we do, and Dr. Ali is with us.
Yes.
So what we are going to do is I just browsed around, and I will just show you a 2-minute video about Michael McGee. Then we open the floor for just an open discussion. If you are okay with this, then we'll do that. What do you think?
I think it will be fine, really. And better than not having anything from Professor Mike McGee.
Okay,
Yeah.
so let me share with you then in this case, if you don't mind. Can you see this? Can you see my the video?
Yes, we can see.
Okay. Is the audio okay?
Yeah, fine.
I'm a professor in chemical engineering at the University of Colorado. I'm also the associate chair of the material science and engineering program, and I'm a fellow in RACI, and I have a joint appointment down at the National Renewable Energy Laboratory. The Department of Chemical and Biological Engineering here has a lot of strengths, but the one that I'll speak to is in renewable energy. And I think the reason we're strong in that area is that we're located so close to the National Renewable Energy Lab, and we're also in Boulder, which is arguably the #1 location in the United States for people who care about renewable energy and sustainability. My group takes full advantage of the National Renewable Energy Lab being nearby. In fact, 2/3 of my group spends most of their time down at the lab. My students, along with our colleagues at NREL, have made a world record all perovskite tandem solar cell that has 23% power conversion efficiency. We've also set some of the records for stability with perovskite solar cells. We can have our cells last for over 1,000 hours at 85 degrees Celsius and 85% humidity. I'm also excited about what our team is doing with dynamic windows. We've made a technology that switches fast and has a very neutral color. We're making the windows larger and larger. And that work is attracting a lot of attention from glass companies, window companies, and automobile companies. People are even thinking of applications for things like augmented reality goggles. You know, the world faces a lot of challenges, but I certainly think one of the biggest ones is preventing climate change. And I think chemical engineers have a big role in multiple ways of generating energy and finding ways of storing energy. And so I really think we have an important role to play in addressing this crucial problem.
So that's it. So
yeah, I just
I think,
yeah.
I think Dr. Ali now should chair this closing session.
Yeah, Dr. Ali, are you with us, Dr. Ali? Dr. Ali?
The video which you showed is exactly what he's doing. Stabilizing the perovskite solar cells, 85 degrees temperature, and tandem solar cells with high efficiency, 26% efficiency, and then the window electrochemism. So these are the three things which you showed. So
it was the right choice for the video, I assume.
Excellent choice.
It was a representative video.
Dr. Ali, are you with us, Dr. Ali?
Yeah, he's with us. Dr.
Yes,
Ali.
yes, I'm here.
This is now, and you have to have this closing session. Inshallah.
Yeah,
so
sure.
You can invite some questions, some general discussion.
Is there any questions for the last panelist?
They asked already the questions as we went through. But I think we may as well, Dr. Ali, if I may suggest, especially after we listen to all of the speakers, those who are with us now, the speakers, if we want to give them a minute or 2 minutes to comment over the whole program, I think that would be useful for the participants. I mean, this is just suggestion.
Like in the form of some recommendations for future.
Okay, so thank you very much, really, for the excellent forum that we had. I'd like to thank you all, speakers, the attendees, for participating with KFUPM in its 16th Saudi Technical Exchange meeting, STEM 2020, in which we addressed the R&D in clean energy challenges and opportunities. I think we had excellent presentation and discussion in which we tackled the topic from different aspects: education and academia, industry. Even we touched upon social and ethical responsibility. We even addressed the integration of these aspects together so we can bring to light solutions that help the people and also our planet. I'd like also to mention that even Saudi Arabia has launched the National Renewable Energy Program, NREP, in an active aspiration to indigenize the renewable energy market in Saudi Arabia with the highest international standard. The program aims to activate our local sources of renewable energy production. It is planned to produce 9.5 gigawatts of energy. NREB is a strategic initiative under Vision 2030 and the King Salman Renewable Energy Initiative. And as I mentioned, that the program also aims to maximize the potential of renewable energy in Saudi Arabia.
The program set out an organized and specific roadmap to diversify local energy sources, stimulate economic development, and provide sustainable economic stability to the kingdom in light of the goals set by the Vision 2030, which includes establishing the renewable energy industry and supporting the advancement of this promising sector while working to fulfill the kingdom's commitment to reducing carbon dioxide emission. So I think those pillar, water, energy, and making our planet clean in terms of the carbon emission and so on, these are fundamentals and they are integrated together. The university KFUPM, as our president mentioned in the inauguration speech, that we really put even forward our education towards digitalization, plus we emphasize a lot also on energy from all its aspects. We have concentration now literally in energy efficiency. We have in renewable energy, we have hydrogen mobility, we have even master professional programs touching upon also sustainable and renewable energy, plus even the material, and we saw how important also the material side of the energy as well. So all of that, I think, give an indication of the importance of this topic, not only for the kingdom, but also the globe, plus also KFUPM in particular. And also, by the way, for even the individual, each of us has a responsibility for keeping even our planet in general safe. With this, I'd like really again to thank all our distinguished speakers from all around the globe. I know that maybe some of them, they have very early in the morning or late at night, and they were really, with their commitment, we had really, I think, an excellent program. And I'd like to end with a quotation from the Energy Secretary, Ernest Moniz, Department of Energy at USA, in which he says, clean energy innovation is the solution to climate change. We don't have the luxury of waiting for new technology to emerge. We need to rapidly accelerate the pace of innovation to meet the climate change. With that, I hope to see you for future event at KFUPM or elsewhere. Hope all the best for all of you, and thank you for the participation with us. Thank you all for participating with us in this event. Thanks.
Thanks all.
Thank you. So, thank you very much. Assalamu alaikum rahmatullahi wa barakatuh.
Assalamu alaikum.
Thank you. Well organized. Thank you. Bye.